Well, we have talked about both glycolysis and gluconeogenesis, specifically with how the enzymes themselves are regulated. We haven't really done a whole lot of comparison and contrasting between those two, and I wanted to kind of just talk about that briefly in this regards. And ideally, if I wanted to talk about the enzymes that kind of play in this tandem back and forth action, I could have started with pyruvate, but I just felt like starting with glucose if I wanted to. And I'll draw the glycolytic pathway in gold and then the gluconeogenic pathway in magenta. This kind of all revolves around the actions that we have of phosphofructokinase and then fructose 1,6-bisphosphatase. If you're going back to my gluconeogenesis video, I think I drew specifically the enzymes for glycolysis in gold as well. So hopefully this is kind of some overlap here. That was actually unintentional. But anyways, let's talk about phosphofructokinase. And I would originally call these things activators and inhibitors, but since this is an allosteric enzyme and it's just easier for me to write, I'm just going to refer to the positive and negative effector molecules. If you don't know what that is, I have a video where I specifically talk about that somewhere in this playlist. But anyways, for phosphofructokinase, the two positive effector molecules, or you can just think of it as allosteric activators, consist of AMP, that's nothing really new that we've talked about, and then fructose 2,6-bisphosphate, that's nothing new either. Yeah, this entire video is really going to be review. I wanted to put everything together to compare and contrast them. But I'm going to talk specifically about fructose 2,6-bisphosphate after I make this one. I'll probably do a separate video explicitly going into detail about that guy. But for now, the negative effector molecules for phosphofructokinase would consist of ATP itself, citrate, and then acidic condition. So what all these things here signify is that the energy of the cell is adequate. We don't need to keep making ATP. We need to shut those pathways off. And by the same notion of what we have activators over here, I think you can imagine for the gluconeogenesis, when we're talking about the fructose 1,6-bisphosphatase, it's immediate contrast with what we have with phosphofructokinase. Just really stressing that that's a phosphatase enzyme that we're talking about here. As far as a positive effector molecules goes, the only one that we have to worry about is citrate. And then for negative effector molecules, we have AMP and then fructose 2,6-bisphosphate. So once we get to phosphoenolpyruvate, the next thing that it's going to react with, at least in terms of glycolysis, would be pyruvate kinase. And for the positive and negative effector molecules of pyruvate kinase, we have, I'm just going to tell you, should probably guess what these are. You should probably know what these are, at least to some extent. But fructose 1,6-bisphosphate as a positive effector, and then ATP and alanine as negative effectors. Really reiterating that this is fructose 1,6-bisphosphate, F16BP. And for the negative, or you can think of it as inhibitors, we have ATP and then alanine. All this stuff we've talked about already to some extent. We haven't really mentioned so much fructose 1,6-bisphosphate, I think, in the last videos, but definitely ATP and alanines as the role that they play with pyruvate kinase regulation. And remember, because we have to overcome M-pyruvate kinase, or just any pyruvate kinase in both the skeletal muscle and the liver, we have to use oxaloacetate as an intermediate for the gluconeogenic pathway. Pyruvate carboxylase and then phosphoenolpyruvate carboxykinase. I think I've actually made videos explicitly for each and every one of these guys. But just to, I guess, reiterate, keeping things looking at the big picture here, both of these guys have positive, negative effector molecules. For pyruvate carboxylase, the positive effector molecules consist of acetyl-CoA. I've already really talked about that, especially I think I made a specific video for it. And then as a negative effector molecule would be ADP. And then the only negative effector molecule that the book mentions, I don't know why I drew it out like that, but for phosphoenolpyruvate carboxykinase as well as ADP. All right, so for the production of fructose 2,6-bisphosphate, this originates from fructose 6-phosphate. Okay, so fructose 6-phosphate gets phosphorylated by another type of phosphofructokinase known as phosphofructokinase 2 to give us fructose 2,6-bisphosphate. And if we wanted to go backwards, we would simply apply the fructose 2,6-bisphosphate to fructose bisphosphatase 2 to give us fructose 6-phosphate, right? So these two guys were kind of reacting in tandem with each other, and depending on the metabolic needs of the cell, you're going to have one of those active while the other is inactive, and vice versa. But what's interesting to me is that these two domains, these two enzymes, both a kinase and a phosphatase, exist connected. They're all a part of one long polypeptide chain, right? Like yin and yang, if you want to think about it. And a part of this is in the N-terminal, there's a regulatory domain with a serine residue, and that's what I wanted to talk about. So we have two enzymes, a kinase and a phosphatase, that do the exact opposite reactions chemically. And the way that we regulate this is at the N-terminus, there is a At the N-terminus we have a serine residue. So I know it's been a while since we talked about this, but keep in mind what serine is involved in, and then the N-terminus in terms of the directionality. I don't think that it's really important that you understand that there's the N-terminus followed by the PFK followed by the phosphatase. I don't really think that that's important in regards to this. But what you may remember from serine is that whenever we have, for example, the cyclic AMP being activated, such as with glucagon, we have protein kinase A phosphorylating serine. All right, so let's say that glucagon has been released. This causes the cyclic AMP cascade, which is going to result in activating protein kinase A. Protein kinase A is going to result in phosphorylation. Or is it going to result in phosphorylation, just in case that wasn't obvious to you, at the serine residue, right? At the serine. So what are the effects of that phosphorylation? So in case it wasn't obvious from the blue color that I'm using here, I'm talking about phosphorylation. So when we have phosphorylation at that serine residue, that's going to result in an active form of the fructose bisphosphatase, and it's going to result in the inactive conformation for the PFK2, phosphofructokinase 2. And by the same notion, if glucagon resulted in phosphorylation at the serine, then dephosphorylation results from the action of insulin, which leads to a higher concentration of fructose 6-phosphate, which leads to an activation of a phosphoprotein phosphatase. So when we have the event of dephosphorylation happening, I think as you could imagine what's going to be the ultimate result of this is that dephosphorylation is going to turn on PFK2's activity. And by the same notion, as saying that this is activating, if we are having dephosphorylation, then it's going to be resulting in inactivation. So it's so interesting to me that dephosphorylation, the action of protein phosphatase, shuts off the phosphatase in our enzyme, and by the same notion, the action of a kinase shuts off the action of our kinase in our enzyme. So it's kind of like yin and yang, or whatever you want to think about it. I always imagine that as a two-headed dragon in some context. I don't know why I think about dragons a lot in this class. But anyways, that's how we regulate the amount of fructose 2,6-bisphosphate